Alright, in this video we're just going to add a couple new skills, one of them being limiting reactants and the other being percent yield. So limiting reactants is basically looking at the fact that you start with the amounts of all the reactants you're using and you check how much product each one can make, then choose the smallest amount of that product and that's the amount you make. It's no different than saying, well, I have so much flour, so many eggs, I have enough eggs for 2 batches of brownies, I have enough flour for 3 batches of brownies, but once I made 2 batches, I'm out of eggs. Okay, so that's all limiting reactants are. Okay, and I think you've worked a few examples of this. We're just, give some examples in notes and, really help solidify that here. Okay, so in this reaction, this problem says if 10 milliliters of 2 molar lead nitrate is reacted with 10 milliliters of 2 molar sodium chloride, what is the limiting reactant and how much solid product will be made? So just like in every stoichiometry problem, we first have to start with a balanced reaction. So I'm reacting lead nitrate with sodium chloride. And this is a double replacement reaction. It's going to make lead chloride and sodium nitrate. You make sure it's balanced. To balance it, I need 2 sodium chlorides and 2 sodium nitrates. Now I need to know what is the solid product. Well, if I look at the 2 products, sodium and nitrates are both very soluble, so that's a very soluble compound. Chlorides are normally soluble, but they precipitate with lead. So lead chloride would be my solid product. That's what I want to find. Okay. Now, normally, if we look at the roadmap, I say, oh, well, I can call like lead nitrate A, and with other problems, lead chloride would be B. So I'm trying to go from volume of A to mass of B. The thing is that I also have an amount of sodium chloride that I need to check against, so we can call sodium chloride C, and I have to go from volume of both A and C to the mass of B. So I really have to do this twice. Okay, so if I start off with the fact that I know I have 10 milliliters, and this is for lead nitrate, I have to go from that to moles of lead nitrate. For moles of lead nitrate, I need to go to moles of lead chloride. And then from there, I need to go to mass of lead chloride. Okay? So I'm going to do that. However, I also have to do the same thing with sodium chloride. With sodium chloride, I start out and I know the volume. And it will go from that to moles of sodium chloride. From that, I need to go to the moles of lead chloride. And then finally, I need to get the mass of lead chloride. Now, one thing I should say here is that really, you don't need to go to mass with both, because really that's extra work. Not like that it's a lot extra work, but really you just have to check here which is the smallest. And once you know which one of these is the smallest, okay, then you know which one you have to use to go to mass. So let's actually do this in practice. We'll look at the next sheet. So again, I'm going to start off with, I've got my reaction all laid out. Okay, so I'm given amounts. I've been given 10 milliliters of 2 molar lead nitrate. I've been given 10 milliliters of 2 molar sodium chloride. The first thing I'm going to do is I'm going to go to the mole of the substance. Okay, so I take the volume times molarity. So the volume is 0.01 liters, that's what 10 milliliters would be, times 2 molarity, and I have 0.02 moles of lead nitrate. From that, I can find out how many moles of lead chloride I would need. So it's a 1-to-1 ratio of lead chloride to lead nitrate. So I would also make 0.02 moles of lead chloride. I need to do the same thing with sodium chloride. Find out, okay, how many moles I have. Since I have the same volume, the same molarity, I have the same number of moles of sodium chloride. However, when I try to find out how many moles of lead chloride I would need to make, because it's a 1-to-2 ratio, I only have enough sodium chloride to make 0.01 moles of lead chloride. So I need to compare these two numbers. Then once I compare those two numbers, I'm going to find, okay, this is the smallest. So once I know this is the smallest, this is the one that matters. So my sodium chloride is now my LR, my limiting reactant. This is my excess reactant. I have extra of it, and I don't care about this amount anymore. I don't want to make sure I'm just crossing out so I don't accidentally use it at this point. Now, because that's my smallest amount, that's the amount of lead chloride I'm going to make. Now I just need to turn it into my needed amount, and I multiply it by its molar mass of 278.1 grams per mole, and find that I can make 2.8 grams of lead chloride. Okay, so let's work another problem. It says if I have 10 grams of sodium hydroxide and I react it with 8 grams of iron chloride, how much of the solid product will I make? So again, sodium chloride is not going to be my solid product. We know that dissolves in water. So my solid product is iron hydroxide. I've got it balanced here for you. We're going to start off with, okay, what are we given? I'm given 10 grams of sodium hydroxide, 8 grams of iron chloride. Because in chemistry, the roadmap says take those lab amounts, turn them into moles. So divide by the molar mass, so 10 grams divided by 40 grams per mole is 1/4 of a mole. Divide by the molar mass of iron chloride gives me 0.049 moles of iron chloride. Now to find the needed amount. The ratio with sodium hydroxide is 1-to-3, so I take my 0.25 moles, divide by 3, and I get how many moles of iron hydroxide that can make. Take my moles of iron chloride here, and it's a 1-to-1 ratio, so it's the same number of moles. Now again, I'm going to compare the moles that I can make. So I compare 0.083 to 0.049. 0.049 is the smallest number of moles, so that's what I'm going to continue on with, saying that I'll make 0.049 of iron hydroxide, and then I turn it into grams by multiplying that by its molar mass to get what I can make. So these are our last skill, percent yield. So when we are working with percent yield, what it is it's telling us what percentage of the amount we expected to make from calculations did we actually make in lab. And so this is something you'll be looking at in lab. You'll always be expected to say, what is our percent yield? And so percent yield is the actual amount you produce divided by the expected amount you should have made, and then we multiply by 100% to put it as a percent. Okay, so in the last example, we thought we would make 5.27 grams of iron hydroxide. If I actually go and do this in lab, I find maybe I only made 4.37 grams. So I take, to get percent yield, I take 4.37 grams divided by 5.27 grams, multiply by 100%, and I'll find what my percent yield is. Normally, percent yield is less than 100%, but you need to make sure you know how to use the numbers. Okay? If you get a percent yield over 100%, you can't say, I did it wrong automatically, because sometimes it does happen. You need to make sure you're always putting the actual amount you made in lab over the expected calculated amount, which is our theoretical yield. It'd be another way of saying what's on the bottom. Okay, so really that's all the new skills. I just want to look at another way of looking at steps rather than doing a roadmap. If you'd rather have like numbered steps of like, how do I solve a stoichiometry problem? I prepared these for you. So the first thing you do, get a balanced reaction always. Okay, very important, because if you don't have the right recipe, there's no point in continuing on. The second step in stoichiometry is get the given amounts you have into moles, unless you already have them in moles. So you go from mass to moles by taking mass divided by molar mass. You can take volume to moles by taking moles times volume. Then once you have moles, find the moles of what you need. So you take your moles of what you have times the ratio of coefficients, get the moles of what you need. Once you have those moles, if needed, you can determine the limiting reactant by choosing between your 2 moles of B, which whenever can be smallest. Once you have that number of moles, finally find the quantity you need by going from moles to mass or moles to volume, depending on what you're asked for. And then finally, step 6, if you need the percent yield, you can then find the percent yield. Okay, so following these steps basically brings you through the same roadmap I'm talking about. It's just a different way of looking at it. You have to decide for yourself. Is it easier for you to draw out the roadmap to know what to do? Is it easier for you to organize things in a table, such as some of the examples I've worked and the way I like to do it and will probably work a lot in class, although I'll try to incorporate a few things? Or is it easier for you to follow this procedure of 6 steps, do step 1, do step 2, do step 3, and so on? You have to decide for yourself what's going to work the best for you to get the problems done, okay? Oh, and there's the stoichiometry worksheet answers that answers the problems you'll be getting, I guess, tomorrow. So I'll put these back up tomorrow. You don't need to write them down now.